Hello everyone, I am Professor Muthana Ahmed and I'll be covering a new course this time. This course is heat transfer. We'll start up with chapter 1. Just cover the basic, the definition of heat transfer, the different types of modes heat is being transferred, such as conduction, convection, and radiation. We'll go through the formulas used and the definitions of it, what they are, the symbols of the parameters that do affect these modes of heat transfer. So let's go ahead and start. What is heat transfer? Heat transfer is the exchange of thermal energy due to a difference in temperature. So whenever there's exchange of temperature, and temperature always travels from hot to cold. So for example, if we take a pot of soup and we put it outside, let's assume that the pot of soup has a temperature of 70 degrees, right? And outside the temperature is 0 Celsius. Okay, now heat is being transferred from the pot of soup, which is 70, it's the hotter object, or it's the hotter system, and it will be transferred into the surrounding, which is the colder system. That transfer is represented by Q. Q is the heat transfer rate, and this course will be focusing on how to find Q. So as you learned in thermodynamics, which is a prerequisite to this course, the first law of thermodynamics, which is the law of conservation of energy, meaning that energy cannot be created or destroyed. It only changes its form. It changes from one form to another, or it's transferred to a different form. So for example, let's say when you eat food, right? That food you ate has energy, and that's what gives you the energy to walk, run, exercise, so on. So the first law of thermodynamics is Q equals delta U plus W. Q, as I said, is the heat transfer, and this course will be focusing on how to calculate the Q. Okay? Whereas delta U is the internal energy, which there's certain formulas you can use to find the internal energy, and W is the work being done in the system. So let's look at the three types of modes, three different ways that heat is being transferred. Conduction is number 1, 2 is convection, and 3 is radiation. Conduction is the transfer of thermal energy from the more energetic to the less energetic particles due to their interactions. So if we assume that I have a steel rod and I apply a hand torch to one end of that rod, okay, what would happen in that end is the particles at that end will gain energy, causing the particles to move around, become more energetic. Okay, that's heat transfer through convection. We'll go through that. But conduction is the transfer of the transfer of energy from the energetic particles to the less energetic, which is on the other end of the rod. So if we assume this end here was heated with a flame torch, the particles at this end will be more energetic. Now the particles being interacting to each other, the heat will transfer in conduction, heat will transfer due to interactions. So it will affect the particles that are interacting or are in contact with them, and therefore in a matter of time you'll find that the not only one end is hot, but the second end eventually will have the same temperature as the first end that's being flamed. And that is what conduction is. Conduction is calculated with Fourier's law. Professor Fourier studied the behavior of heat transfer, and he found this law here to how to calculate heat transfer in particles, in materials. Heat transfers in materials. So he found the Fourier's law of heat conduction, which basically states that the heat rate per unit area, which is also called flux, okay, equals to negative K. Negative K is a property of material, or it's also called the thermal conductivity. So in order to find it, you need the type of material and the temperature it's at to find K, times dt dx. Okay, Q is the heat rate, which has the units of watts. Q double prime, that's the heat rate per unit area, meaning that the heat transferred in a given unit area, okay, which is also called flux. So if we assume that if we draw an example of a one-dimensional heat transfer in a wall, this here being our wall was length of L, okay, this will be our T1, this is our T2. Temperature will always transfer from hot to cold, therefore there's a linear heat transfer, okay, decrease in temperature. dt is basically T1 minus T2 right here, and dx is L minus 0, okay, the final length minus the initial length, which can also be written like this, okay. Therefore we substitute this back into our Fourier's equation, this one here. Heat rate per unit area at the x direction equals negative K times T2 minus T1 over L, which also equals K T1 minus T2L. Okay? Therefore, Fourier's law can also be written this way if we're not using a differential. Okay, it can also be written as Q double prime equals K delta T over L. Now, to calculate the heat rate from the flux, you basically just need to times it by A. Why? Because flux, as we said, is the heat rate per unit area, and if you times it by area, you'll just get the heat rate. Okay? So the heat rate will equals this according to Fourier's law. A is the normal area, or you could call it the cross-sectional area that the heat is being applied in, or the heat is transferring through. Okay? Now the second mode of heat transfer is convection. In convection, heat transfers between a surface and a fluid. Okay, surface and a fluid. In order to understand the heat transfer in convection, you need to have a background with fluid mechanics. So if we look at this schematic here to my left, that is the behavior of a fluid velocity traveling through a system. So we notice that the velocity closer to the system is lower. Then as we get higher away from the surface, the velocity is higher. So if we want to study the temperature behavior along a surface, we'll notice that close to the surface the temperature is higher, and as we further apart from the surface, we'll notice that the temperature decreases. As we, like for example, if we have a heated steel plate, right? At the surface, that's where it reaches its maximum temperature. But as you move away from it, you'll notice that as you move your hand away from that surface, you'll notice that the temperature is decreasing and decreasing until you reach a point where the temperature is the same temperature as your surrounding. Okay? The equation used in convection is Newton's law of cooling, which states that heat rate equals H times A times Ts minus T infinity. A being the surface area, where H is the convection heat transfer coefficient, which depends on fluid property, the geometry, and the flow regime. The geometry of the surface. Is it a plate? Is it a cylinder? Is it a rod? Okay, is it a rectangle? And the flow regime, is it turbulent flow or laminar flow? And the fluid property, if it's oil or water, mercury, and so on. So in chapter 6, 7, and 8, okay, we'll teach you how to find H. You cannot find that at the back of the book. Unlike K, the thermal conductivity here, in order to find K, all you need to do is have the temperature and the property, okay, the material, and you can go back at the back of the book and get the value for the thermal conductivity. The heat transfer coefficient, convection heat transfer coefficient H, needs to be calculated. Some roughly estimations for H, for the H for gases, the convection coefficient for gases is relatively between 25 to 250 watts per meter cube Kelvin, whereas for liquids the convection coefficient is between 100 to 20,000. And that's why when you want to, for example, cool an engine, it's best to use liquid than gases. But in the radiator, they'll use, for example, air. But to increase the convection heat transfer to cool the radiator, they usually add fins, and that we'll go through that in later chapters of how to increase the heat transfer or the heat rate using external factors such as fins. Okay, and that is it for convection. For radiation, it occurs in a vacuum. Radiation is calculated through the Stephan-Boltzmann law, which basically states that flux, the heat transfer per unit area, equals sigma times the temperature of the surface to the power of 4. Sigma is Stephen Boltzmann's constant, which is 5.67 times 10 to the power of -8 watts per meter squared K to the power of 4. This is for an ideal emitter called a black body, okay, or a black surface. For non-black bodies, the only difference is the surface emissivity, okay, where the surface emissivity is between 0 and 1. If it's 1, you'll treat it as a black body. Okay. Now, radiation heat transfer between a small object and the walls of a larger enclosure, for example, as a dime in a closed room, that can be calculated using this formula below, which is heat rate per unit area equals the emissivity coefficient times sigma times Ts to the power of 4 minus T surrounding to the power of 4. Ts is the temperature of that system inside the closed system, okay, and the surrounding is basically the temperatures outside the system or at the walls of the system, because the temperature will hit the walls and then come back, so it will affect the temperature of the small object itself. Okay, that is it for the first class in heat transfer. Stay tuned to the next one.